Hello everyone, thank you very much for clicking on this video. It's me Apisha. In this session we are going to learn about elementary continuous time signals. What's that? Why we are studying about that? In fact, characteristics of systems are being studied by applying elementary signals into its input and analyze corresponding output. So if you want to do that, we should know about different types of elementary signals. That's what we are going to do in this video. Here we go. Let us first focus on one of the most important elementary continuous time signal, which is none other than unit step function. It is represented by u of t and mathematically defined as 1 for t greater than or equal to 0 and 0 for t less than 0. This is the waveform. The independent variable t is plotted along x-axis and the signal value is plotted along y-axis. You can see the signal value is 0 for t less than 0. At t equal to 0, the signal value changes suddenly from 0 to 1. After that, it is having a constant value 1. So, it is clear that unit step function is discontinuous at t equal to 0. As I told you, elementary signals are used to study about systems. Now, I will give you an example which illustrates the significance of unit step function in network analysis. You can see a RC network here. A 1 volt source is applied into this network through a switch. From the symbol of switch, it is clear that it remains open for t less than 0. At t equal to 0, it is getting closed and remains in the same closed position for t equal to 0 to infinity. So this RC network is getting an input 0 for t less than 0 and 1 for t equal to 0 to infinity. Hence, we can replace this 1 volt source and this switch with a unit step function 1 into u of t. What's the advantage of that? In fact, if we replace this source and switch with unit step function, our mathematical analysis becomes very simple. Got it? Moving on to next function, unit ramp function. It is represented by r of t and defined as t for t greater than or equal to 0 and 0 for t less than 0. You can see the waveform here. Independent variable time is plotted along x-axis and signal value along y-axis. It is a straight line with a slope 1. Now what we are going to do is we are going to express r of t in terms of u of t. Do you know how to do that? U of t is defined as 1 for t greater than or equal to 0 and 0 for t less than 0. R of t is defined as t for t greater than or equal to 0 and 0 for t less than 0. By comparing these two expressions, we can write unit ramp function r of t is equal to t into u of t. Our next task is to find derivative of unit ramp function r of t. As you know, for t greater than or equal to 0, r of t is t, correspondingly its derivative becomes 1. And for t less than 0, r of t is 0, hence its derivative is also 0, which is nothing but u of t. So we can write d by dt of r of t is equal to unit step function u of t. Hope you got it. Let me now take you to next function, unit parabolic function. It is represented by p of t and defined as t square by 2 for t greater than or equal to 0 and 0 for t less than 0. You can see the waveform of p of t here. Then by comparing expressions of p of t and u of t, we can write p of t is equal to t square by 2 u of t. What's our next task? Our next task is to find derivative of p of t. For t greater than or equal to 0, p of t is t square by 2, hence its derivative becomes 2t by 2, that is t for t greater than or equal to 0. And for t less than 0, p of t is 0, hence its derivative is also 0. And this function is nothing but unit ramp function. So we get d by dt of p of t is equal to r of t. Okay? The next function I have for you is impulse function. It is represented by del of t. It is having a non-zero value only at t equal to 0, and integral minus infinity to infinity del of t dt is 1. Del of t is 0 if t not equal to 0. This is the waveform. You can see del of t is 0 for t not equal to 0, and at t equal to 0 it is having a non-zero amplitude. In fact, impulse function is not a practical function, but we are using it for the analysis of signal and systems. Next, rectangular function. It is defined as pi of t is equal to capital T for mod t less than or equal to t by 2, 0 otherwise. This is the waveform. You can see it is having a constant amplitude capital T from minus t by 2 to t by 2. It looks like a rectangle. After that, triangular pulse function, it is defined as del a of t is equal to t minus mod t by a for mod t less than or equal to a, 0 for mod t greater than a. You can see the waveform here. It looks like a triangle. The next function I have for you is Signum function. It's an important function from analysis point of view, which is defined as Signum of t is equal to 1 for t greater than 0 and minus 1 for t less than 0. This is the waveform. You can see the signal value is minus 1 from minus infinity to 0. At t equal to 0, what happens? Signal value changes suddenly from minus 1 to 1. That is, signum of t is discontinuous at t equal to 0. And for t equal to 0 to infinity, it is having a constant amplitude 1. Got it? Let me now take you to next function, sinusoidal signal. It is mathematically defined as x of t is equal to a sine omega t plus theta, where a is amplitude, omega frequency, and theta phase angle. This is the waveform. Okay. Then we have real exponential signals. It is mathematically defined as x of t is equal to a e raised to at. Here we have two constants, capital letter A and small letter a. These two constants should be real, then only x of t becomes a real exponential signal. Now we are going to plot x of t. First consider the case a greater than 1, then it will be a growing exponential which looks like this. You can see the independent variable time is plotted along x-axis and the signal value along y-axis. The signal is having a value a at equal to 0 and it is a growing exponential. What does that mean? It means as time goes on, the signal value increases exponentially. And for a less than 1, it's a decaying exponential which look like this. Here also at equal to 0, the signal value is a, and as time goes on, the signal amplitude decays. Got it? Let us move ahead and see what is complex exponential signals. It is represented as x of t is equal to e raised to st, where s is a complex variable which is defined as sigma plus j omega. Sigma is the real part and omega is imaginary part. In fact, complex exponential signals are very important from analysis point of view, since if you are doing analysis using these signals, mathematical operations like differentiation and integration become simple multiplication and addition. By substituting the value of s in x of t, we get x of t is equal to e raised to sigma plus j omega into t. That is equal to e raised to sigma t into e raised to j omega t. As you know, by using Euler's relation, we can write e raised to j omega t as cos omega t plus j sin omega t. Correspondingly, x of t becomes e raised to sigma t into cos omega t plus j sin omega t. Now what we are going to do is we are going to plot complex exponential signals for different values of sigma and omega. Okay, the first condition, sigma is equal to 0, omega is equal to 0. Correspondingly, we get x of t is equal to e raised to 0 t plus 1 plus j0, that is 1, which looks like this. You can see it is having a constant value 1 from minus infinity to infinity. Hope you got it. Let us move ahead and see the second case. Omega is equal to 0 and sigma not equal to 0. Hence we get the value of complex variable s is equal to sigma and x of t as e raised to sigma t. For sigma greater than 0, it will be a exponentially increasing waveform like this, and for sigma less than 0, it is exponentially decreasing waveform like this. Then the third case, where sigma is equal to 0 and omega not equal to 0, correspondingly we get x of t is equal to e raised to j omega t, which looks like a sinusoidal waveform. Finally, sigma greater than 0 and finite omega, it will be an exponentially growing sinusoidal signal, which look like this. You can see the amplitude, the peak amplitude of the sinusoidal signal is increasing as time goes. So we are at the end of this session. Hope you all enjoyed it. If you have any doubts, please do let me know in the comment section. Thanks for watching. Thank you.